Welcome, everybody. I'm speaking very loudly because we're not running through the microphone. Um, Welcome to the HCIL Brown Bag Lunch. We have many visitors today from our College of Education. So hope you all say hi to them. We have many shared interests, even if we don't realize it. The reason that we're coming together is to hear from Dr. Mitchell Nathan, who's visiting us from the School of Education at the University of Wisconsin-Madison, where he is the Vilas Distinguished Achievement Professor of Learning Sciences in the Educational Psychology Department. He's got affiliate appointments in the Department of Curriculum and Instruction, Psychology. He's also chair of the Learning Science Program and principal investigator in the Wisconsin Center for Education Research and a fellow and founding officer of the International Society of Learning Sciences. Also an inductee of the University of Wisconsin's Teaching Academy, which promotes excellence in teaching in higher education and is on its executive board, and one of the founding members of EMIC, International Group of Scholars and Educators focused on embodied mathematical imagination and cognition, and director of the very evocatively named Magic Lab, I love it, where he and the members of the lab study how people think, teach, and learn with particular emphasis on the role of language, gestures, and embodied processes and what they play in mathematical reasoning and meaning for formal systems. So without further ado, let's welcome Dr. Nathan.
Thank you, and it's nice to have this quite varied group. I'm going to let you know now, this is a little bit of a invitation to the students who are here, which is the first student, when it's Q&A, the first student who asks me a question will get a free copy of my book. So I brought it. It's Foundations of Embodied Learning, a Paradigm for Education. So a little bit of incentive for student involvement. I want to talk to you today about embodied design principles for mathematical reasoning and how they have an empirical basis and how we can build a theory that can lead us to a very valuable and intriguing set of design guidelines for fostering thinking and learning. So I owe this work to many people who are at various points more and more scattered across the globe. So at some point, I'll be talking about research involving all these folks. And as a general theme, my driving question of the members of this lab is, how can we best educate embodied minds? Like once we recognize the embodied nature of human cognition, what do we do differently? How do we take advantage of these things? How do we play into the role that these embodied processes play as we think and learn? So one of the things that really focuses a lot of my work is this question of how do people make meaning from arbitrary and abstract symbols and procedures like they occur in math or in many of the other scientific and technical fields, right? How is it that I can look at a string of symbols and markings and understand that they have meaning, understand there are things I can do to them, understand I can use them to describe and model the world, even predict the world, right? And even invent new such symbolic representations. And my answer is that we ground symbols and procedures by relating them to our lived experiences. And in particular, our embodied experiences arise as a particularly accessible form of lived experiences. The idea that we exist in a fixed corporeal body with certain kinds of symmetries and certain kinds of asymmetries. We operate in certain ways in three-dimensional space. We perceive time in certain manners. All these things come into play with how we are in the world, how we interpret our experiences of the world. And we use those as the founding, fundamental grounding in which we understand new things. So for example, a teacher trying to convey early ideas about algebra will take advantage of the fact that her students understand notions of balance, right? And showing these relationships which we see when we videotape classrooms, offers a grounding experience for students to relate to these things. They can start to see the equal sign in particular as not just an operation that's producing something, but as relating to expressions, to quantities, to different things. They don't even have to look the same to achieve balance, right? So once we recognize this importance, we can start to ask, what are the implications of this for understanding how people reason and learn in various STEM fields, science, technology, engineering, and mathematics? And how do we best design educational technologies and learning environments to take advantage of these processes? So think of this kind of problem, right? This is a really typical problem from a high school geometry textbook. This is the vertical angles theorem. It's actually a super important theorem, comes up in all sorts of technical settings. And it basically is this claim that if these two angles are what we call vertical angles, which I know they don't look vertical to you because we think of vertical this way, but in this case, the word vertical means formed by vertices, not formed through top and bottom, but formed by vertices, prove that these two angles are congruent. Right? And students get asked these kinds of questions all the time. And this is often what we want students to somehow generate, but that's not what students actually do when we give them license. So here's where we hope all our technology works. So here's a video of a student answering this question.
Assuming the lines are straight and we're operating on a plane, the lines are if one of the opposite angles was different than the other opposite angle, then the lines would not be straight. They would be there would be an angle at the intersecting point in one of the lines.
So what I want you all to notice, what I want you all to notice is how much gesturing and body movement played in this process, in our being able to articulate this reasoning. In fact, in many ways, in being able to do the reasoning itself. And the fact that we have these plastic, pliable bodies that we have ready access to, our hands and our arms, allows this person to essentially generate a set of mathematical objects that this student can then operate on and explore and use it to get at a deeper understanding of a universal property of space and shapes, right? And we see the student actually doing this really cool thing where they're like taking their hand that's otherwise this taken to be a straight line and then like doing this weird thing where like, oh, it would have to do something like this. Like it's this beautiful proof by contradiction. We can map a lot of the students' arguments to actually the arguments that Euclid even laid out in the Elements book and see that it's an extremely logical, thoughtful way of going and really different than the kind of reasoning we saw in that two-column proof, right? And we see this among students and even among teachers all the time. We enlist our bodies, we enlist the physical worlds around us to do this thinking. We even enlist the bodies of other people, right? This is a group of pre-service teachers, and they're all trying to do some theorems around circles, and they realize, however good I do my hands, I can't make a circle. But if I have like a whole bunch more hands, I can make a much better circle. And then I can actually use one of my hands to do things like explore central angles and chords and things like that. And so we have these resources, and people make use of them. The alternative is really interesting. What we ask of students is to take these, what I would call highly regulated diagrams. We're supposed to only write them in certain ways and label them in certain ways. We have these ungrounded symbols. They don't tell us what they mean, and they are confusing. Like the thing that says angle 2 and angle 3, these what we might think of as like, oh, that should be so many degrees. That's not true. These are actually indices of these angles, right? They refer to the angle, not to the measure of the angle, which is what this refers to. Math is full of this stuff, right? And it's very confusing. Math symbols in and of themselves become obstacles to mathematical reasoning. But they gain power once they're understood, once they have meaning. Then we use them as these simplified notations, and it allows us to do much more advanced forms of reasoning. We can do it more quickly. We can also write computer programs that can process them, which are hard to do if we're just doing this, right? So there are many ways of thinking about all this stuff. And then the other thing that I find fascinating with things like proofs is they often end up being a series of completely static declarative statements. There's never like an action that actually ever gets said. Each thing is just about some relationship. But that isn't how we tend to think about things. We often tend to think about things, and you could really see it in this student's video. He's exploring the relationships. Like, I'm going to vary this thing. I'm going to make it straight. I'm going to make it unstraight. I'm doing all these actions and operations, right? And it's through this process that I gain a much deeper understanding of which properties in this system, in this case, two simple lines, which properties are variant and which properties are invariant. And in the end, I want to be able to identify those invariant properties because those are the universals that I want to be able to articulate for a proof. So when we have all these ungrounded symbols and we ask students to do them and we never give them the experience to do that grounding, we don't see students just freeze, right? They do what for them is intelligent behavior. They do their best. They think, I'm going to interpret this the way it makes sense to me. I'm going to manipulate these things in certain ways. I'm going to apply the thing I think they mean and refer to, and I'm going to go through those processes. It leads to a lot of mathematical errors. It leads to a lot of like teachers scratching their heads being like, how did this person get from this to this, right? And we've explored this question before. Philosophers have explored this question before. So in particular, John Searle offered this thought experiment, which humorously he called the Chinese room thought experiment, right? Because somehow like nobody knows Chinese. But his idea was actually very intriguing. If I put a person who doesn't know Chinese in this room, and I give them inputs that come in these Chinese characters, and I give them this vast ledger that tells me that anytime I see this kind of symbol, I produce this symbol. And anytime I see this symbol, I have a list of 8 other symbols. I can choose any one of them. I pick this one and I output it. And I do this ad infinitum as a stream of symbols comes in and I create the next stream of symbols that go out. Does this person know Chinese? Right? He asks it this rhetorical question, right? Does the person outside the room think they're talking to a Chinese native speaker, right? It's a very intriguing set of questions, but where we've landed on this is that this person does not understand Chinese. Why don't they understand Chinese? Well, because there's much more to meaning making than simple token to token rewrite rules or associations, right? That's not the core of what it means to understand language, right? But now we're building systems, right? We're building these high dimensionality large language models and other kinds of systems that are essentially doing that. They're saying, I've got sets of tokens, I've got the context in which they co-occur, I've got their frequencies, I've got all this massive embedding space that I can map all these things to. I can look at their sort of quote distances apart from one another, and I can pick words that make sense because they co-occur closely with other words. And we can ask ourselves, well, maybe it's close enough, and maybe we don't, we can't really introspect about all that we do in our minds, right? A lot about our thinking is completely unavailable to us. Maybe that is what we do. And so a group of psychologists have asked this question. Well, if people do those same tasks versus computers, do they end up with the same sort of thinking? And they did this wonderful study where they found words that have extremely close co-occurrences and they swap them in sentences. So a computer processing it in some kind of LLM form, like latent semantic analysis, HAL was another tool they used, would it find these sentences interpretable, and what would people say? And they asked people to basically rate them on how sensible the sentences were. So an example from their corpus is, after wading barefoot in the lake, Eric used his shirt to dry his feet or his glasses to dry his feet, right? And they found that shirt and glasses have extremely small dot product between the two of them, so they tend to come up in a lot of the similar circumstances. And of course, human read this and they're like, well, it's one sentence makes sense, and another sentence completely doesn't make sense. But LLMs don't really pick up on this. Now, there have been some benefits lately with self-attention, if people know how that mechanism works, that makes LLMs do that a little bit better. So they're finding ways to kind of like circumvent some of these problems, but it shows how quickly these problems arise and how fundamental they are. And what Glenberg and Robertson concluded from a series of studies is we're not just looking at these tokens, we're looking at the affordances of these tokens. What is it that the word shirt and glasses afford? What actions and contexts and perceptions and associations do I have beyond just linguistic, right? That make it make sense or not make sense. And so we, oh, I thought there was another slide here that I guess it got disappeared. Okay, all right. So this started to raise this question about how do understanding or perceiving language relate to the actions we associate with language. And so there's this notion in psychology of the perception-action loop, that we really shouldn't think about perception as separate from action and action as separate from perception. And I really find this study very compelling. So this is with infants. I think they're about 6 months old. And they are going to use either one of these two kinds of teethers, right? They're going to put these in their mouths. Infants, I'm told, infants love this. No, my infants also loved it. A is what they call a flat teether. And among the other things it does, of course, it reaches all the gums, but it also blocks the tongue from reaching the top of the mouth. Whereas this teether, if you see with this U shape that it has, it does not do that tongue interference. The question is, if we teach infants certain sounds, certain phonemic sounds, which they wouldn't normally have encountered in their lives, and we want to teach them to discriminate between two very similar phonemic sounds, and one group of infants has this teether that blocks their tongue, and the other has a teether that does not block their tongue, an action, right? Blocking or not blocking an action. Will that affect how they perceive auditory speech sounds? So what did they do? They gave infants in America who are not familiar with Hindi dialects these two different letters, and I'm sure there's probably people in the audience here who could do this. I can share with you. Will I be able to jump to a web page? Is that gonna? Okay, I can't just like go to it. Can I just okay, it won't show up there. Oh, I can grab it. All right, let me see where I find it. So I'll bring this across if it will go. Hello. Maybe go the other way, huh? Okay. Bring this across. Oh, it's not. It's gone from my window though.
You can start over there. Hold out to the top.
Okay.
Yeah.
Got it. It's like in between.
Yeah,
Okay.
yeah.
All right. So this da and ta, right? So it's right here. I was able to find this. It's going to read all of these. There was a website that just had these two, but we're going to really look at these two in the middle, the third and fourth consonant sounds.
H, d, d, n.
Okay. So those, I'll play it again.
D, h, d, d, n.
Right? And one of these involves the tongue's mobility and the other less so. Okay, so now I want to, do I have to drag it or can I just switch screens?
Just pick up
Can I do that? Okay, great. Right? So the paradigm is this. This is a common infant paradigm. You play these things multiple times. What happens is infants get bored if they keep seeing or hearing the same stimuli, and they show some kind of surprise, which means they have a longer looking time when they find an event surprising, right? So that gives you a way to discriminate if they're hearing this, if they can tell if they're hearing the same sounds, and if they don't. And it turns out that when you use these flat teethers, you impair their ability to engage in the same level of discrimination of these sounds. We use our bodies even to process what we're hearing. If that act would cause us to make a motor movement in order to make that discrimination. So it's this perception action loop in process. And we see it even more dramatically even with adults. So here's a picture of a brain and with emphasizing areas around word and language recognition that's spoken. What happens when we tell people, when we present auditorially, while they're in a scanner, the words kick, pick, or lick, right? All very similar phonetically, but they all relate to very different motor systems in the body, right? And what Pulvermuller and colleagues found is that when we hear these words, we tend to activate the motor systems for kick that involve leg-related behavior. Arms are active, arms and hands for pick, and face and mouth related for lick. We don't just hear words and process them in some simple auditory loop. We do this with action and perception combined, and that is how we understand words. We essentially ground the meaning of words by listening to them and relating them to our prior experiences, action-related kinds of phenomenon, right? In this case, actions in the motor cortex. And we can take this even further. We have early readers. Early readers sometimes struggle with meaning making. And they struggle in particular to make inferences. How do you make an inference, which means you try to extend beyond what the text actually said literally to make a plausible inference about what could also be true? So if I move an object and it has an object on top of it, an inference would be that the object on top of it also moved and is now also in the new location, right? Readers have to start to learn to understand that that is the process of reading comprehension, that you build this rich model of what the words are saying, what they mean, and how they relate to the various states of the world they're describing. So they gave people these passages, like, for example, this one about the farmer, and one group had little Fisher-Price toys of the farm that they could follow along with the story and move the objects around, and the other group did not. And they found, and the other group, they actually, to equalize the amount of time, had that group just read the passage twice, right? Or hear it twice, depending on their level of reading. And what they found was that they achieved much better understanding when they got to move those little toys around consistent with the movements of the story. They also found that they could take the toys away and train people to do the imagining that those little toys were moving around, and got them to kind of like wean away from the particulars of the toy system to learn things and to start to relate the behaviors of what stories tell kids. So we can start to see the really powerful role of the body in understanding things, right? And this has to be actually one of my favorite studies. So this Botox injection study, right? So they had people who were coming into a clinic. So they already were coming. They got them to do a series of sentence interpretation. Then they got their Botox injection, and then they came back a couple weeks later and gave them some of the same sentences. What's intriguing about the sentences is that they have affect. These are sentences that all express some kind of emotion: sadness, anger, happiness, right? So here we go, 20 sentences, happy sentences, 20 angry sentences, 20 sad sentences. They get the Botox injection, they come back, and they recorded their reading response times. What happened was they found reading times declined. I mean, they took longer. Reading times took longer, sorry, for angry and sad sentences after the Botox injections, because they affected this muscle right here, the corrugator supercilius, which is what we do when we're sad or angry. We frow, what is it called? Furrow. We furrow this brow. It's the corrugator. In fact, we have that word in cardboard, right? Corrugated cardboard. It's the little ripples, right? It's the little ripples that we make, right? And people don't like those ripples. They don't want to show that they have those ripples, right? It affected the reading times for angry and sad sentences, but not for happy sentences, right? This is a case where doing some kind of medical intrusion actually is affecting comprehension processes. Now, it's temporary, but something to think about. Which is to say, how do we experience emotion? Do we just process the words and we come up with an affective output? Or is it that we actually live the emotion? We actually instantiate it with our state of our bodies. And that's how we understand why someone else is angry or happy or sad. I'm going to jump ahead, so it's tracking time here. So this got me very intrigued about these questions about grounded and embodied learning. And so I set out to try to understand how could we do this, and how could we do this in an area of advanced mathematics? There's a lot of interesting work on embodied mathematics with really young kids, and they're doing counting and they're doing early arithmetic and things like that. I'm like, what about really advanced topics like abstract reasoning, like you have in mathematical proof? Mathematical proof, you have to take information in, synthesize it, establish some kind of universal statement that's generalizable, that's logical. And so I'm going to run through a series of studies about this. And I chose geometry because sometimes geometry is a little bit like the stepchild of math, at least in math education research. There's a lot of research on arithmetic and fractions and algebra, but not so much on geometry. But when you start to look and poke around geometry, you realize geometry affects every field. It affects art. It affects political science. Like in this book, Shape, which is a great book for math nerds out there who like to read popular books on math. He has a whole section on gerrymandering and how that came about. He has a whole section on virology and vaccines and how they're all about geometry. If you remember COVID-19, it was all about like blocking the shape of these places where these viruses could attach, right? This is all in the intriguing area of geometry. Material science is all about geometry. So it's a really profound thing to try to understand. What I also liked about it is proof doesn't have set strategies. So there's all these areas in math that I know students and we all don't understand very well, but we have really well-honed procedures that we can use. Like long division is a really great example. Like people don't really know how long division works. They just know they can do it. Multiplying by fractions, they know they can flip and multiply, or dividing by fractions, they know they can flip. They don't have to really understand the math to execute them. They can just punch things in calculators. They can do these well-practiced procedures, but proof isn't that way. You have to just formulate a proof from your own understanding, and everyone's going to come up with a slightly different one. So I'm going to relay something like 7 laboratory and classroom studies kind of quickly, just to give you a sense of the range of things that are going on. But what I want you to see is the interplay of theoretical, empirical, and design principles all through the lens of embodiment. So one was a pilot study we did. We asked people to think about this triangle inequality conjecture. For any 2 triangles, the sum of the lengths of any 2 sides must be greater than the length of the remaining side. Okay, and we asked people to go up to a whiteboard and touch the spaces on that whiteboard. And when they got to the X, they switched hands, right? So that's the top group, which we call the control group. The other group did these spots simultaneously, and in so doing it, not only created a triangle with their bodies, but at some point, we scaled things so that it would be slightly greater than their hands could reach in the farthest pair of dots, which brought their bodies all the way into the board, right? And we wanted them to have that experience of that kind of like degenerate triangle being like 2 parallel lines, essentially, right? And we asked, is this going to help people think about the proof of this mathematical conjecture, right? And we theorized that it can, because what happens is we not only have actions that relate to our concepts, but we have concepts that relate to our actions, that there's a reciprocity that goes on between our action states and our cognitive states, so that when I learn new concepts, I tie them to embodied experiences. But if I can recreate those embodied experiences, I will also recreate those concepts in the minds of our students, right? So this is this action cognition transduction, that they can move reciprocally between the 2 of them. And we find that not only did it help them achieve proofs more readily, but it also showed up in their explanations. They started making these gestures in accordance with their treatment. It was part of their conceptual structure of how they thought about the mathematics. And so here we see like these very convincing graphs showing like there really is a statistical advantage of doing these actions over doing the matched actions. So then I started with my team looking more deeply. Let's just look at all these gestures that people are making when we give them all these conjectures. What are they creating? What is it that they're doing? What role are their bodies playing? And we see people starting to make triangles. They start to make quadrilaterals. They start to explore the ways areas can shift. They start to actually do these kind of transformational things because the body is this extremely valuable set of resources. You can do a lot with it. So, so we asked them now to do the following, and you'll see this paradigm kind of coming over and over again. We give people mathematical conjectures about geometric objects, and then we ask them, we try to collect data on 3 different things. One is we wanted to know their intuitions. So intuitions are these snap judgments immediately. Do you think it's true or false? Before you do any thinking, before you engage in any body-based resources, what's your impression? We want it like in the first second that they see it, right? True or false snap judgment. Then we looked at their insight. As they articulated their thinking, what's the sort of gist? Like, are they at least talking about triangles when they're talking about a triangle thing? Like let's give them some credit for this, getting the space correct. And then we had this very stringent criteria, which we called transformational proof, which is to say, it's a form of deductive proof. Can they demonstrate operational thinking, that they, the actions they perform, they expect to have certain outcomes? Can they generalize so that it applies to all of the thing they're talking about, all triangles, all circles, all cones, whatever the object is? Are they demonstrating their thinking is generalizable? And is it logical? Do they show a chain of logical inference, right? So that if they didn't get all 3 of those criteria, they do not get credit for a proof. So proof is a very hard thing to achieve. Insight's far easier. And then intuition, it's a 50-50 guess, right? We also looked at these gestures. And in particular, we looked at a class of gestures that we started calling dynamic gestures. So yes, gestures all involve some kind of movement, but dynamic gestures are interesting because they actually transform the thing that is being gestured. So tracing a triangle is not a dynamic gesture because it's just getting at the static properties of that triangle. But if I start to consider all the ways I could tweak a triangle and explore whether properties hold or don't hold as I do that, as I grow and shrink and skew and manipulate a triangle or a circle or whatever, those are the kind of things we were really interested in because those start to look like embodied simulation. They start to look like I'm bringing these imagined objects into my own space and manipulating them with my bodies as a vehicle for trying to think through the reasoning. And so we asked this question, first correlationally, do we see this kind of gesture behavior when people are engaged in geometric reasoning? And we engaged experts who were math majors and graduate students in math and non-experts. So these were non-STEM majors in an ed program, right? So we had basically 90 of these people. And we gave them these various kinds of conjectures. And then we said, you know, let's look at their movements, right? Let's look at their intuitions, their insights, and their proofs. Let's monitor their gestures, and then let's look at the content of their speech. And we hypothesized that dynamic gestures might help with intuition, might help with insight, might help with proof, and we also might see this category of speech where they're talking about the actions. They're describing them in words, what we call operative speech. And we looked at this across various levels of expertise, spatial reasoning, verbal fluency, ethnicity, gender, age, and prior geometry knowledge. So I want to share with you, this is a video, it should be. Oh, here we go. Okay, so anyway, this shows that yes, not only does spatial reasoning and gesture production predict their performance. But when you add gesture into these models, it actually bumps out spatial reasoning. So what essentially was happening was, if you engage gestures during this, even if you're kind of low spatial reasoner, you're going to look more like a successful reasoner than someone who has high spatial reasoning, who might not be using gesture. So gestures almost offer this externalization of spatial reasoning that we often think of as a completely mental process. So let's see here. So I thought of really taxing you all because the first minute is this, but I'm going to jump ahead. But I want you to know this is the world I live in, where I watch videos that are mostly silent, because literally it's not till a minute and 1 second that this person relates. So here we are.
This is
Oh, sorry. It redid it.
this is false, because if you have a triangle that has varying lengths, like all the lengths aren't the same on all 3 sides, the mid segments would therefore not be parallel to the 3rd side.
Okay. Can you explain more about what?
This was a great move, by the way. The investigator just said that. Keep that in mind when you use those, so you collect data. Because now look what happens.
You have a triangle. If you picture a triangle that's flat on the bottom, you have a very, very long side going up and a short side, and a shorter side on the other side. It would like not. Actually, I'm going to change it to true.
Okay.
Yeah, because if you take the mid segments of a triangle, it would be parallel.
Okay.
Can
you explain why you changed your answer?
Well, I guess I pictured it in my mind, and it made more sense to think of it like that. I don't know if I can say anything more.
Okay.
So we start to get information about these models. When we can do logistic regressions on these behaviors that relate gesture and speech to proof performance. And we can see that what happens is, in fact, we can not only show the relationship of these things, but we can start to imagine that we might even be able to do interventions that could elicit the kind of movements we want to have, and those could lead to the kind of thinking we want. So then we started cultivating lots of actions from successful embodied proofs and building them into a video game where people then had to follow the movements of avatars on screen, and we track their movements in real time. And when we started tracking their movements in real time, we could use it as a way to prompt certain kinds of geometric thinking, right? And then we could also record their movements as they were happening, right? So we get these kind of skeletal kind of images. The first round we used Kinetic. Some people might recognize this kind of data. Now we're using stuff from Google that gives us more information. And, and so then we started coming up with these tables where we could track these relevant actions against different mathematical conjectures and see if they would lead to improved performance, right? So here's an example of the kind of data we're getting. And then we get these kids like doing all these awesome movements. And we found, in fact, that these dynamic gestures not only are predictive of the proof, but these are large effect sizes, like effect sizes of over 1.0. I don't get them that often. Like they're pretty substantial effect sizes, we also see this kind of transformational operational speech showing up as also predictive. And in fact, what's really cool is we can start to then see, well, what led to the gestures? Well, what led to the making the gestures that are helpful is giving them these dynamic directed actions and having them copy them. And the people who did them were the ones more likely to make those dynamic gestures. Again, very high effect size of D, D.8. And then once they make those, they have this very high likelihood of giving a correct proof. It also led them to make more of these transformational speech kinds of statements. So that proved to be very successful. So then we started wondering, oh, could we get students to perhaps create their own embodied movements, their own directed actions, right? Could we give them little tools that they could then manipulate the avatar into movement sequences and have other students play those games and see if it would help other students learn those things? So we built this kind of manipulable avatar, right, that they could then do these sequences and then had them play the games in their classrooms, right? And then people are like copying the avatar movements from the players. And we found that it not only helped the students who were making them because they were going through this design process, but also that ideas would start to travel through the class through embodiment. Like I wasn't telling another group this new mathematical idea. I was just sharing with them actions that they could play, and they now understood that mathematical idea the way our group understood that mathematical idea. So you have this sort of version of transfer that was like the travel of ideas across groups. Then we realized we really needed to simplify the technology because instead of having it be this thing where we click on joints and move stuff, we now wanted to just see, could we just get people moving in front of the screen and recording their movements and having that be the trained way to then do it. And so we had to kind of simplify everything. And this is the state of things as it is now. And then where are we going with this? We're now collecting a lot of this real-time data, right? We're collecting all these, what we call landmark data against the hands, against the torso, against the face. And we're doing all this multimodal analytics to try to find if we can do some kind of automated coding and look for regularities in our data that we could train transformers with. So I think I have a few more minutes. Am I doing okay? Or?
16 minutes.
Okay. Okay.
How much do they want to use?
Yeah. Why don't I stop here and take some questions? And again, first student asks a question gets a book.
That was the offer. I missed that part. Sorry.
So one second. Why don't they switch audio streams? So if you mute your audio,
Okay.
your microphone,
So just go here and do I just click on it, I think?
Sixth question. No. Is it working? Yeah. But it goes on there. Okay. Yeah, I have, ooh, now I don't like the sound of my voice on that. Okay. A couple of questions, I guess. I'm trying to think of which one might be best asked. With the work that you are doing, I noticed that you were sharing a lot of the results quantitatively, right? Like looking at effect size and stuff like that. I was curious if there were any qualitative, like obviously you're watching measurement and doing observations, but was there any sort of qualitative analysis to look at some of the things that happened with the students and their own understandings versus just like coding and looking at different like amounts of change?
This is very much what I would call mixed method.
Mhm.
Get to those models, we do a lot of qualitative. So these are very much mixed methods. To get to those quantitative models, we're doing a lot of qualitative analysis of their movements and their speech. And, so we're doing like heavy duty discourse analysis and heavy duty gesture analysis and coming up with those descriptions. As far as than like taking individuals and interviewing them or something. Like one of the things that's kind of interesting about embodied learning is how much flies under conscious awareness. So one of the intriguing things, which I didn't report on here, but is in a couple of my papers, is how often people who engage in these movements, if you ask them, do you feel the movements you did related to the mathematics? They're like, no, it didn't have any relationship, right? And even just to be safe, well, sometimes like anyone who said yes, even if like their explanation is super weird and doesn't sound plausible, we would just exclude those. We just like would run the analysis again and just say, well, they said it did, so let's take them out. And honestly, in a group of 100, you might get like 10 or 12 people at the most who say that. But if you take them out, it doesn't eliminate the effect. Like, so one of the things that's very interesting, and I do talk about a lot in here, is how we have a lot of conscious processes that are involved in cognition and a lot of unconscious processes that are part of cognition. And in a lot of our education, we don't attend to a lot of those unconscious processes a lot, but they're really important in areas like mathematics and thinking, because they're involved in like pattern matching, perceptual processes, like a lot of things we do fly under our conscious radar, but they do affect our cognition. You know, we just aren't aware of them. So here you go. Congratulations. All right. Here, a question here. Or do you want to call on people?
Yes, I want to follow up on that question, but it's a great question. Oh, okay. So my follow-up question is from a qualitative perspective, like there's the sort of effects on learning and like the consciousness of like this is helping me learn. But I'm very curious about the affective experience and the perceptions of myself as a learner, my relationship to mathematics, like is mathematics for me, like all that sort of like is in the discourse, but like, it's yeah.
I think those are really great questions. What I can tell you very anecdotally is when we bring these video games into the classroom, students really have a fun time playing them because they love like moving and dancing and doing all this stuff in front of the camera and seeing these skeletal versions of themselves moving around. And then they get to see other people do the actions that they're doing. We haven't done any kind of in-depth thing to like get at their affective states that they're doing as yet, but the newest work I'm doing, which I could talk about just really briefly, is this idea of augmented intelligence. So the idea is essentially to say we need to acknowledge that AI systems like LLMs, for example, are very limited in their ability to understand human interactions, human behavior outside of like pure text, right? But they're really good at doing a lot of vast pattern matching and finding these latent patterns in these data. They're also really good at not blinking ever, right? They have incredible perseverance of their ability. So if we want to find, like we saw with this one participant, a moment of insight triggered by movements and maybe with facial and other nonverbal cues, it's a lot to ask teachers to pay attention to that. But we can get AI agents tracking that. And if we can train AI agents to notice at least that there's an event, even if they can't categorize those events accurately, the idea is to then alert a human. So this is where the augmentation comes in. So these are human AI systems. You alert a human, you build detectors that are trained from people like me watching these videos saying that was an insight event. I want to flag that, but I don't know what features matter. I'll let the AI multi-dimensional scaling and embedding space like sort that out. I just know it was significant. But then you alert a human to do these like what we call data-driven interviews and get at the antecedents and get at the emotional states and get at the cognitive states of the people. And that's the current work I'm doing right now with Ryan Baker and Stephen Hutt and Michael Swart. So we have an NSF grant looking at that right now.
All right. I will take Connie's question, and there's a fun comment in the Zoom chat as well.
I have like disjointed brain soup. I'm thinking like the implications for encouraging pro-social behavior with this sort of thing. From a maybe Machiavellian sounding standpoint, like this makes me think of like Socratic questioning in the bottom half of your little model where you had like the gestures and then you had like the thinking out loud part. To me, that's like Socratic questioning and like the social conditioning, like how people will train people around them like dogs. Like, we're going to do this now. We're going to welcome these people into our spaces. So that sort of like, how do you think, has that ever shown up when like the students are making things for other students? Like, this is how we do this. We do math this way. And like, do you think that you could take the sort of games you're making for math and use them to train people into pro-social behavior and sort of analogical thinking as a way to be good people?
I mean, if I say yes, does that satisfy your question? I think you're getting at a really nice quality of what's kind of holistic about being a human, right? And one of the things is that we pay attention to others and we sometimes emulate what they do, especially if we want to belong to that group. So we attend to those practices as well as those verbal utterances, but also mannerisms, right? And that I think that does influence internally our cognitive states and our affective states, right? And so those are ways of, like, if you want to pick an example, pick a path, thinking like a mathematician. It might be like, well, maybe we shouldn't ask people to think like mathematicians. Maybe we should ask people to try on being mathematicians, right? So it's not just about what you say and what you write. And that's probably true with art, and that's probably true with science, and it's probably true with athletics and a lot of other things. One of my early music education experiences was with a very prominent cellist, and he first moment of the first day of class, he brings in a cello and he picks people and he's like, go play the cello. And they're like, that's why I'm in this class. Like, I don't know how to play a cello. And he's like, but how would you play a cello? You've seen people play. And they get up and they play. And he's like, that was pretty good. Like, and they're doing all the, this and whatever. And he's like, yes, that's how you play, like, let's not make it this thing where I have to show you a bunch of scales for a month and then talk about modes and then talk about and then like you never touch an instrument until like week 10 or something. He's like, you're all going to play by the end of today, and the rest is just like, let's go further. Right. So we don't do that so much with the mathematics and science fields, but we could and we should. And a lot of times that does happen in like enrichment kinds of environments, but those don't get to as many people. So we need to do those in schools. Does that help answer your question? Yeah. Yeah. So I know you have a comment and then you're someone.
So we have a comment that there's rich philosophical corollaries for all of this, from Plato's Meno to Alfred North Whitehead's aims of education. We see a lot about how intuition, mimesis, rhythm can reveal underlying forms of thought for learners and unite subjective and objective aspects of learning.
Yeah. That's a really great connection. Yeah. Right. Right. And for whoever this person is, also, my work is also influenced by Merleau-Ponty and Heidegger and others, who I think are also influenced by those people you mentioned. So yes, please.
So I think my question kind of builds nicely on the holistic example you just gave. And I'm curious to, when it comes to some of like the neuroimaging or like the gesture stuff, what, if like any studies out there, like what happens when these studies are focused primarily on mathematics? What happens when we start bringing in other content areas into the mathematics? Like, is more stuff lighting up? Is there deeper understanding because they're embodying not just the math, but maybe another potential component? So when we start making learning more holistic, what happens to the body?
Yeah, really great question. And you probably saw at the beginning, a lot of the foundational research I was citing was more in like language and reading, right? Math kind of trails along. But if you look kind of historically, especially in education literature, we know like the most about reading and language in terms of like how people think and in terms of children's development. We know sort of second about math, and then all the other fields kind of trail along, with a fairly large cliff from reading, math, then all the way, like we just know a lot less about them. It has to do with, I think, a number of things, but one of the things I think it has to do with is there's something about how close language and math are to our way of just the way we are in the world. And then other areas have this too. I think some areas like music, right? But other areas are like almost, I don't want to make anyone who's like a scientist or a social studies person, but they sort of rely a lot on those fields to do what they do, right? It's hard to do science without any math. It's hard to do science without any language. It's hard to do social studies without any math. It's hard to do social studies without any language, right? So a lot of times what the research literature will do is try to target these more foundational capabilities and also find ways to simplify the object of study, right? So in the end, I think that people are, for example, very much using language systems when they're thinking mathematically. They may also be very much using mathematical systems or spatial systems when they're reasoning about language. And I think it just amplifies even more, like more touch points in the network as you move to these other content areas. I think that really learning is largely very holistic, and we do make all these connections, but we also have to do some, like, if you will, pruning. Like every time you encounter a word or a concept or a visual input, you acted on all of the associations, you would not be a very functional person. It's hard, right? A big part of cognition is inhibition. A big part of successful intellectual behavior is figuring out what to direct your attentional resources to and what to sort of put to neglect, right? Or reduce. And so that's another part of what it means. So the models may kind of show this enormous web, but at some point, and often if we have some neuroscience people in the room will know, within a couple hundred milliseconds, even within maybe sometimes as fast as 50 milliseconds, we start shutting down many of the associations. And that's probably a good thing. And people who have trouble doing that can have more trouble just in general, like learning things, I
think we have time for one last question, and Sam has had his hand up for a while. So
hi, thanks so much for this talk. I think the simple version of my question is like, what is the base for the propositions that you're asking people to prove, and like what's the kind of geometry that you're asking people to learn in these studies? The expanded version of the question is a lot of like you mentioned, like learning upper level mathematics, where learning that there are different modes that math can happen in, that there are multiple geometries that you can do depending on what you're trying to do, is a really important part of like mathematical seasoning or whatever. And I'm wondering, oh my God, I'm blanking, but it seems to me that like when you're doing these physical gestures, on the one hand, it would seem like it would be naturally fit for learning like Euclidean geometry. But at the same time, mathematics has been taught where you have like certain set tools. What can you do with a straight edge? What can you do with a protractor? Have you all worked with like, how do you learn like non-Euclidean geometry? What are the gestures that people do when they're trying to communicate these like higher order or just like different geometrical concepts? Yeah, that's my question.
Well, I haven't done any studies per se, but what I do think comes out from some of this work is that people aren't actually in their core being Cartesian. So people rather not think about, if I go to you, I do a vector here, and then I do a vector there, and then I look at the resultant vector and stuff like that. I think people are like more like radial kind of systems, which I don't know if you'd call that that's not maybe non-Euclidean, but we don't live in many non-Euclidean spaces, but we do live in lots of non-Cartesian spaces. And I think it helps us understand. So I do have one project I didn't talk about with Yulong Zhang on learning vectors and learning vector arithmetic. It's way better for people to think in radial kind of coordinate system than to think in a Cartesian system about vectors, because I just think of myself as the origin, and vectors just emanate from me, right? Rather than I think of, oh, I'm here, but the origin's there. I have to now translate whatever relationship I want to that origin, and then do that, and then do the trigonometry. It's like the trigonometry just is like, oh, I do that, with my body, super simple. So I think it does invite notions like body-centric forms of geometry, and how that relates to other areas of mathematics, like say calculus and things like that. I think it's probably worth saying we don't really have a good cognitive reason for spending the first 12 years of mathematics in linear math, knowing that the world is absolutely not linear, and that you have to like bang your head against the wall to find examples of things that are truly linear, because they're very, very rare, and they only occur during really small portions of their behavior. The world is curves and fractals and stuff like that. And I have a feeling people actually can learn those things really well, and then see linear as a special case of those things, and that we would do well to think about the mathematics as one of curves and surfaces and things like space filling and things like that, and then show that there's all these special cases of like planes and straight lines and 0 point masses and things like that. So I don't know if that speaks to your question, but yeah.
All right. Well, I brought us a few minutes over time, but wonderful to have all this discussion. Let's thank Dr. Nathan again, and try this next week.